Hello everyone, my name is Ahmed Assaf. I am an ophthalmology professor at Ain Shams University, Cairo, Egypt. I am happy to be with you in this prestigious meeting. Though online, I hope next time I will be with you in person. IOL power calculations have come a long way since their inception in the 1950s. The early days of regression analysis gave way to more sophisticated formulas, such as the third-generation formulas that took into account corneal power and axial length. Today, fourth-generation formulas are being developed that incorporate even more variables to increase accuracy. It is important to note that while these formulas have greatly improved IOL power calculation accuracy, they are not foolproof and can still be affected by measurement errors. In the early 1940s, Harold Ridley, a British ophthalmologist, observed that pilots who had acrylic plastic fragments in their eyes during World War II did not experience any adverse reactions. This led him to explore the possibility of using acrylic plastic as an intraocular lens to replace the cloudy natural lens removed during cataract surgery. In 1949, Ridley implanted the first IOL into a patient's eye. The lens was made of perspex, a type of acrylic plastic, and was sutured to the iris. While the surgery was successful, there were challenges in selecting the correct power for the lens. Ridley used trial and error methods to determine the appropriate power, which resulted in some patients experiencing postoperative refractive errors. Despite these challenges, Ridley's work paved the way for the development of modern IOLs and revolutionized cataract surgery. As early as 1909, Goldstrand's model eye quantified the refractive power of the human eye primarily from the refractive properties of the cornea, lens, ocular media, and the length of the eye, based on 6 eyes. In 1967, Fyodorov and his team were the first who set up a Vergen's formula to estimate the optical power of an IOL. Now let's talk about the evolution of corneal power measurements. The ancient Greeks were renowned for their innovative scientific and medical practices. One of their earliest techniques involved smoke and mirrors, which may seem primitive by today's standards. The Greeks would direct a beam of light onto the eye and observe its reflection through a mirror to measure the curvature of the cornea. This information was pivotal in determining the refractive power of the eye and the development of corrective lenses. Although the method was not flawless, it demonstrated the Greeks' ingenuity and dedication to progress in the field of optometry. Later, keratometry works by focusing a circle of light on the cornea and measuring its reflection. The amount of distortion in the reflected image is then used to calculate the curvature of the cornea. This elegant yet simple principle has had a profound impact on the field of cataract surgery. It has enabled the diagnosis and treatment of a wide range of eye conditions with superb accuracy and precision. Plácido disc was invented by Spanish ophthalmologist Antonio Plácido in 1880. Unlike keratometry, which measured only the central portion of the cornea, the Plácido disc allowed for measurement of the entire corneal surface. Corneal topographer and OCT have revolutionized the way we diagnose and treat eye conditions. They provide more accurate and detailed information about the shape and curvature of the cornea than ever before. The corneal topographer, for example, uses Plácido disc principle to project a series of rings on the surface of the cornea. With a sophisticated algorithms, a detailed map of the cornea's surface is created, can be used to diagnose various corneal conditions and corneal power calculations. OCT uses light waves to create a cross-sectional image of the cornea, allowing us to see its layers and detect any abnormalities. Axial length measurement has its own milestones. Only when ultrasound measurements of the eye using A-scans became available in the 1970s did improved Vergen's formulas allow for a more accurate calculation of the IOL. The first eye ultrasound measurements were performed in an applanation or indentation mode, where the ultrasound probe was directly placed on the corneal surface. This inevitably led to a deformation of the cornea and the anterior chamber. Using ultrasound, the signal's echo time is measured in seconds and converted into distance millimeters using an average sound velocity. Proper conversion is only feasible if the individual proportions of the underlying model eye and the individual velocities match. Yet, ultrasound biometry depends on the handwriting of the examiner. This in turn leads to different measurement results and thus to incorrect calculations of the IOL. Ultrasound A scans measure the eye's total length, anterior chamber depth, and crystalline lens thickness. To calculate the corresponding IOL, additional keratometry measurements are needed. This procedure should only be performed by experienced personnel. Today, it is not regarded as a gold standard anymore. The disadvantages far outweigh the benefits. Today, ultrasound biometry is mainly restricted to cases where optical biometry cannot be performed due to opaque optical media. Until Professor Adolf Förcher published his groundbreaking results on the optical non-contact measurement of the eye by partial coherence interferometry in the early 1980s, the measurement of the eye by ultrasound as an acoustic biometry procedure was considered completely undiscussed as state-of-the-art. This was changed by the use of light with low coherence, as described by Förcher in 1982. Based on this patent, Carl Zeiss Meditech developed the first biometric device using this novel technology, the IOL Master. With this device, optical biometry became a successful method. For the first time, a technique was available that allowed for distance-independent biometry, providing fast, non-contact and reproducible, significantly higher resolution biometric data of the eye. Nevertheless, the definition of ultrasound biometry as the gold standard has never been revised, and modern biometers are still calibrated according to ultrasound even today. For the first time, a non-contact optical A scan was made possible. Thus, it represented the first interferometric measurement of the length of the eye. This device provided all eye data needed for IOL calculation. For the first time, it was possible to determine both eye length and keratometry data in one measurement performed with one device, so the corresponding IOL calculation can be carried out directly at the biometer without entering data from external sources. In addition, optical biometry is much less susceptible to disturbances such as the filling of the posterior eye, vitreous, silicone gas, or the artificial lens when measuring pseudophakic eyes. In 2008, Zeiss Haag Streit launched the LensStar on the market, which provided partial distance measurement for the first time. Today, most modern biometers work with OCT non-invasively, and a variety of devices are offered that measure the eye using optical biometry. The number of eyes, which is not measurable by optical biometry and thus reserved for ultrasound measurement, is steadily reduced through sophisticated optimization of the measurement methods and is now well below 5% in industrialized nations. Finally, biometry formulas. Along with this technical evolution, numerous formulas have been developed for calculating the optical power of each respective IOL. With empirical formulas, the IOL power is derived from a series of biometric data without any anatomical or physical background. The theoretical optical formulas, which are most commonly used today, extract the IOL power from a paraxial optical model that simplifies the eye to linear Gaussian optics. With modern ray tracing settings, Snell's law is applied at each refracting surface within the eye, and the best focus position is compared with the position of the fovea. However, this requires reliable information on the entire shape of all refractive surfaces, including the corneal front and back surface, IOL front and back surface, and refractive index. More theoretical formulas were derived around the 1980s and 1990s. For example, SRK, Hofer Q, Holiday, and Huygens used several variables to improve IOL calculation. More formulas are becoming available like Holiday 2, Huygens, Barrett Universal 2, Olsen, and many more. The question is how these formulas differ from each other. They differ in their ability to estimate the effective lens position in the pseudophakic eye based on preoperative biometry, interpretation of corneal power from the measured front surface radius, various offset values for biometric values or fudge factors, different refractive indices for ocular media, different vertex distances for postoperative spectacle correction, IOL constants. These are the most commonly used formulas in Europe without history of refractive surgery. In conclusion, today, optical biometry is regarded as standard diagnostic tool and essential basis for IOL calculation prior to cataract surgery. It's an indispensable part of ophthalmology. It has fundamentally revolutionized cataract surgery. However, the ongoing improvement of optical biometry over the past 2 decades led to patients with higher expectations regarding the refractive outcome after cataract surgery. Due to the more precise measurement results of modern optical biometry, patients' expectations can be met far better than by ultrasonic measurements, as the IOL calculation is much more accurate. By implication, modern and sophisticated IOL concepts, such as EDOF lenses, accommodating lenses, or applying the principle of monovision, have become possible only by optical biometry with its high reliability and enhanced IOL calculation strategies. Thank you.